Welcome to this video. In this very long video, I'm going to show you what is NumPy. I will give you the basic ideas of NumPy and concepts of NumPy, like the NumPy array and the most important NumPy functions. And I will lead you step by step into the kind of thinking of using NumPy in practice for data science problems. This tutorial is completely based on my book, Coffee Break NumPy, which I have co-authored with two of my former colleagues at University of Stuttgart in Germany. And yeah, we are happy to present you the book, which has just launched. If you are interested in getting a very thorough NumPy education, because you want to start out with data science and don't miss out on the machine learning and data science train, then you are welcome to check the book out. I will give a link in the description. Otherwise, yeah, enjoy the video. Just try to the video comes with a lot of puzzles. First, I will start with a small tutorial. Then I will give you a series of puzzles and how to solve these puzzles. And yeah, just try to think about the puzzles, guess the answer of the puzzle, and I hope you have fun with the video. So enjoy. So what is NumPy? NumPy basically is a Python library that allows you to perform numerical Python. Yeah, Pi is for Python, obviously. Yeah, I won't write Python. No worries. Okay, so NumPy stands for numerical Python. And NumPy is a Python library that allows you to perform numerical calculations. Think about linear algebra in school or university. NumPy is a Python library for it. So it's about matrices and vectors and performing mathematical computations on these matrices or vectors. Yeah, like maybe we have a matrix like this, 1, 0, 0, 1, and 1, 1. And for example, we want to do a matrix multiplication. So we have I don't know, this vector, and now we multiply. So now we have this vector, and no, sorry, I have to get rid of this one. Yeah, now we can multiply this, perform this computation, yeah, like matrix multiplication. Sorry for being confused. Okay, so we have we multiply 1 times 1 is 1 plus 0 times 0 is 0, so we have our first value is 1. Then our second value of the vector will be 0, because 0 times 1 is 0, and 1 times 0 is also 0. Then we have 1 times 1 is 1, plus 0 times 1 is 0, so we have 101 as the resulting vector. Yeah. So NumPy allows us to do these and much more complex computations, like linear algebra computations. Everything. So at the heart of NumPy basically is a NumPy array. So we have this NumPy array is nothing but a one or multi-dimensional vector like this. Yeah. So we can have a one-dimensional vector which consists of like numerical data values along one dimension. We call these dimensions axes. Then we can have two-dimensional arrays. So we have like here 0, 0, 0, 1, 1, 1, 0, 0, 1, for example. Now for this two-dimensional array we have axis 0. Okay, so we can have a two-dimensional NumPy array which consists of two axes. Like the number of rows is usually denoted as axis 0 and the number of columns as axis, not axis, axis 1. Okay, so we can have two-dimensional arrays, and then of course we can have multi-dimensional, higher dimensional arrays or matrices, and we can perform all kinds of operations on these matrices. So NumPy is a very basic library for data science and machine learning. And if you dive into machine learning, you will see that most machine learning packages like scikit-learn, or even sometimes TensorFlow, even kind of data science focused packages like pandas, all these Python packages, all these frameworks, they are based on NumPy. For example, pandas internally uses NumPy, or they need NumPy arrays for kind of basic pre-processing or post-processing of the arrays. So NumPy is, I would say, NumPy is the basis. It's a very low-level library. You can do everything with it, basically. You can implement all your own algorithms with it. This makes it kind of the fundamental piece of knowledge you need to understand the higher level functionalities or higher level libraries that, for example, provide whole algorithms. NumPy usually won't provide you with algorithms, but you can implement all algorithms with the NumPy library. Okay, so NumPy is really basic understanding for every data scientist and machine learning engineer. And if you're just starting out, it's a good recommendation that you start learning NumPy, start learning the mathematical foundations of NumPy, and then you can move on to higher level libraries like TensorFlow or pandas. Okay, so before we move into a thorough introduction of the NumPy library, I just want to give you a small example that shows how important NumPy is. So for example, suppose we want to achieve, we want to plot something, yeah? So visual data analytics is very common nowadays, yeah? So we have, So if you have some data sets, you usually want to explore the data set, yeah? And you want to kind of, for example, if you have extracted some insights of large data sets, you need to communicate these insights with your boss, for example, or with your clients or customers. Kind of, it doesn't help just to have the knowledge and have maybe the result of the data. You need to communicate the data in order for the data to have any impact with the real world. So you need to plot data. How do we plot? So first of all, let us import the NumPy library, and then of course for plotting we use the matplotlib library and the pyplot module as plot, like this is usually. And now, for example, suppose we want to now in order to plot, we need to have some x and some y values. Yeah, we will define the x value and the y value in a moment. Then of course we can have a nice plotting style, xkcd, and now we plot, for example, yeah, just plot some just plot multiple lines. Yeah, so this is an example from the book. Okay, so we plot the quadratic function, we plot the linear function, and with different styles, and we plot the cubic function, yeah, with another style. You don't have to actually get what I'm doing here. I just want to show you. Okay, so if you now these are the three plots which we plot in a single function call, so to say, and yeah, in each plot we define the x values and the y values, and the y values is basically is a function of the x values usually. Yeah, if you have functions, they are a function of the x values. Okay, now our x values should be some should range maybe from 0 to 1 with step 0.1. Yeah, and now you can already see that we use the NumPy library to define our x values. So we want to have, if you print x, let's comment this out. If you print x, you can see that it evenly distributes the the numerical values in this interval between 0 and 1 exclusive. So it with a step size 0.1. Okay, so this is a functionality. This is an example where we use NumPy in order to plot things. NumPy is kind of the basis for many different other libraries like here. Yeah? Now actually our main objective is to plot something, but we have to use NumPy in order to write clean and concise Python code. Okay, now so let's plot it. Okay, we have some plots, some lines and plots. Here the quadratic function and the cubic function and our linear function, and we use NumPy to define the interval between 0 and 1. It's a very simple application, but it shows you that NumPy basically will interplay in many different areas, not only directly for data science or implementing your own algorithms or even machine learning, but also for very basic tasks that you need to get done if you are doing anything with Python, like plotting or graphic stuff. Okay. So what are arrays and matrices in NumPy? Okay, in this example here, you have already seen that arrays are basically similar to what you know. So they can be matrices, like here we have two-dimensional matrices, we have n-dimensional matrices, they can be vectors. So, but if you're a bit confused by these different terms, don't despair. In NumPy there's only one term, and this is the NumPy array. Or in short, it's often in many tutorials simply call it array. Okay, and we have this array. It can be 1 to n dimensional, and this with one concept to rule them all. And now these arrays can have different data types. Like usually in computer science, you would draw an array like this. We have this box. And how can I draw a line? Okay, here. And then we have some small boxes within this larger box, and this contains some data. Yeah. So for example, now this could contain a string, like a small string s. It can contain an integer value like 42. It can contain a float value like 21.3. So this is float. This is integer value and string. It can even contain some complex values, complex numbers, like you have this, I don't know, 2 plus I, something like this. It can okay, I think that's more or less it. So we can have different values in the array and fill the array and the NumPy array usually. So theoretically, we could add all these values in one NumPy array, but NumPy internally will remember for any array what data type this array is, basically. Yeah. We can define different data types. So for example, if you define an array of integers, then NumPy will recognize that the array is full of integers, and yeah, it will convert all the values to integer values. So if you don't explicitly change the data type of the array, then NumPy will assume that you will use a NumPy array. Okay, so how that you will use an integer array. Okay. So how do we define an array? It's very simple in NumPy. We simply use the constructor array. We pass some for example, a collection like a list or an iterable, and this is the basis of our array. And now this is the simplest form of defining an array. If we print the result of the array, you see, okay, we get back this one-dimensional array which we have defined previously. Yeah, but now in the constructor we can also change the data type of the array. Like we can use the dtype parameter and use, for example, integer with 16 bits. And now if you print a, then nothing changed because it's still integer representation, but we can print the d type, now you will see that the d type is int 16. Okay, not surprisingly, we have defined it as an integer value, and so in this case you don't see any difference to the default behavior, but but now if we pass integers and we basically want to create a float array, we can also specify the float, like 64 for example, bits, and the float data type. And now if you print it, what will happen? Yeah, correctly, it will internally convert all the values to float values. Yeah, you can see this at the small with a small dot notation here, and also the data type is returned as a float 64 data type. Okay, and now has this any relevancy? Okay, first I will show you, for example, if we say we stay with the integer data type, and now we do some metrics, we multiply like a times print a times NumPy array of, no, maybe keep it simple. So we multiply a element-wise with 2.0. You will see this element-wise multiplication and the asterisk operator we will handle later in more detail, but I just want to show you why the data type has some influence on your NumPy computations. Okay, so here we multiply this integer array and we multiply it with 2.0. So NumPy internally will create a NumPy array of type float and multiply it with our integer array. And of course, if you multiply an integer with a float array, then the result will be a float array, because float can have higher precision. Yeah, we can, for example, we could have multiplied it with 2.1. And yeah, you see that now the float is the only data type that is able to represent the outgoing data type. Okay, so important thing to remember: NumPy hasn't. You can create NumPy arrays. You can put in some data types. Okay, maybe let me quickly add one interesting thing. If we, for example, if we make this a float, but we define it to be an integer, then it will do the conversion for us. Now you can see it just rounds, or I think maybe it may use, maybe let's check whether it round or it just use the absolute value. Yeah, it just uses the absolute value, so it doesn't round, it just rounds down, you can say. Okay, so yeah, it will internally convert to the data type. And of course, every NumPy array can have only one data type, so you can't have this homogeneous type of array. One exception is an array of integers, for example, with floats in it. Yeah, so we have this array. Now we print b and we print the type of this array. Yeah, and now you can see that something strange happens. We have this representation u11, and we have an array of strings basically. Yeah, so it has converted the array to an array of strings and not integers anymore. Okay, even if you have a two-dimensional array, say we have this behavior, like we have one dimension is so one row is full of integers and the other row is full of strings. It's filled with strings. Okay, now what happens then? Again, everything is converted to integer. Okay, so this was also for me new. I just wanted to check it out, but you can see that a NumPy array has one associated data type, and it internally converts the array to this data type that is specified by either explicitly or implicitly in your array creation routine. So in the last example, you have seen that NumPy arrays have some restrictions. You can define a data type, and this is associated to the NumPy array. A second restriction of NumPy arrays is the following. So NumPy basically does not only store like here we could create a list the two-dimensional array, yeah, consists, so basically at this point we have only created a list of lists, yeah, and it's a Python representation. And of course a list of lists can have a heterogeneous number of values, yeah. We can have something like this. One list can have many values, and maybe 8 values, and the other list can have only 4 values, and this is totally acceptable for Python, but it's not acceptable for NumPy. Because now you see, okay, it just takes as data type for each element, it's a kind of a two. Now this is a one-dimensional NumPy array, and it as with 2 values, and the first value is a list, and the second value is also a list. And basically you cannot do anything with this representation. Yeah, it doesn't help you a lot. So NumPy has a restriction that in any dimension, so that you have an homogeneous number of values for every dimension, kind of, yeah. So within any dimension, this means that you have this orderly, you have a matrix shape, yeah. You will have, for example, 3 values in dimension 0, and then for all in axis 0, and you won't have something like this, that you have many values, many more values along one axis than you had along the same axis for another index along the other axis. Now this was complicated expressed, but you can see visually what I mean, yeah. So you have this homogeneous array. You have, for example, a 3x4 array or 4x4 array, and then this means that you have 4 values along this along one dimension, or 3 values along one dimension, and this will not change. You won't have suddenly, this will not happen that you have 5 values along one dimension. Okay, so now let's have a look at a code example. So now I want to show you, so this is called the shape of a NumPy array. So say we create a NumPy array with some data, 2, 3, 4. So this is a one-dimensional array, and now we can use the ndim property for number of dimensions, so now ndim property, number of dimensions, and the result is 1. We have only one dimension. So what happens if we create an array? An array 1, 2, 3, and say 4, 5, 6, and we print the ndim property of this array. Then we have the result 2, yeah, because we have 2 dimensions. So the general rule of thumb is the number of opening brackets gives your dimensionality. Okay, so this is one property that can be extracted from the shape, but every NumPy array basically also has a shape, an explicit shape property, and now we will print this shape property of both arrays. Maybe let's first print it for the first array, and the second array you can then think about what will be the shape for the second array. Okay. So here you see, this is the shape property which we have printed, and basically it's a tuple, and every tuple value reflects the number of values along one dimension. Yeah, so we have kind of the first dimension, and we only have one dimension. Therefore, it's a tuple with only one dimension. This strange notation with this is simply a tuple with only one value. It could not write the. So this one would not be a valid representation for Python, because then it would just internally skip the brackets and we would have an integer value. So therefore Python kind of writes for the reader of the Python output, it just represented a tuple with one value as with this strange syntax. Okay, but it's a tuple with one value, and the value gives the number of values, the number of elements in this axis. Yeah, so for example, if you print the shape of the B array, so here we have, of course, we have 3 values and we have only one axis, but now in this case the B shape is a bit more complex, because along one axis, the axis 0, so the column axis downwards, we have 2 values, we have 1 and 4, we have 2 and 5, and we have 3 and 6. So we have 2 values along the axis 0, and we have 3 values along the axis 1. Now let's check whether, Now let's check whether this is actually the result. Also, yeah, we have 2 values along our first axis and 3 values along our second axis. Okay, so our shape, the shape tuple is really important information because it encodes multiple pieces of knowledge. The first is the number of axes, how many tuple values are there. This gives you the number of axes, and then it gives you some information about the axes themselves. So an individual axis, for example, axis 1, how many elements do we have in this axis? Okay, so in the 3-dimensional area will be kind of similar to this example. I can also give you one. Let's have a 3-dimensional one that this really makes sense for you and you understand everything properly. I don't want to rush over this because it's a basis of many more advanced algorithms and features in NumPy. Okay, now what we are doing is we create a 3-dimensional area. So we have 3 opening brackets. Basically, we have 2 2-dimensional matrices in row. So we could also write it like this. Of course, we have to get rid of the 9s. So, okay, yeah, we have. So this is a 2-dimensional array and a 2-dimensional array. So we place 2 2-dimensional arrays in row. And now the shape should be. So we have 2 elements along the first axis. Yeah, like we have this 1 element, which is a multi-dimensional array itself, and here we have another element. So our basic shape should be 2. Should start with 2. Okay, now think about what is the second value of this shape tuple. Okay, so the second should be so we have 2 elements within each of this two-dimensional So now we look into one 2-dimensional element, and we see that this 2-dimensional element has 2 elements. Each one is a 1-dimensional NumPy array. So we have 2 elements again, and then the third one, of course, will be 3 elements because we have 3 integer values here. Okay, now let's check whether this was correct. Yeah, we have 2, 2, 3. Okay, so this is kind of how the shape property works. It really helps to use the opening brackets as a heuristic. So you have the number of shape, or the number of axes is defined by the number of opening brackets basically, and then if you look at the first opening bracket, then the elements in the first opening bracket, then we have the first axis dimension. Then when opening another opening bracket, then we have the second axis, and the third opening bracket indicates that we are now in the third axis. Yeah, so if we have 3 values here, this means that we have number 3 at the position, or the third position of this tuple, this shape tuple. So in the last section, you have already learned how to create basic arrays. Yeah, we use the NP array function. We give some list or list of lists or list of lists of lists, and this helps us to create arrays. We can even specify the ND-type property, yeah, the D-type property, and yeah, that's basically the basic creation of NumPy arrays. The problem is, what happens if you want to create, say, thousands, very huge, massive, multi-dimensional array with thousands of values along every dimensions. And to this end, we have NumPy provides some basic array creation routines that will make it very easy for you to create NumPy arrays. Okay, so now how can we create a how can we initialize a multi-dimensional array with, say, 10 values? So say we want to have 5 dimensions and 10 values along each dimension. So now and we want to initialize everything with zeros. And the intuitive function is the zeros function. We have to specify the shape of the array that, which we want to have, and only by giving the shape it will initialize the array for us. Yeah, so we don't have to define the lists or the collections or the lists of lists and so on. We don't have to give some initial values explicitly, but it does it for us. Okay, so let's make it even simpler. Say we want to create like a two-dimensional array with 10 values along each dimension. Okay, I know I promised you another one, but I just want to show you how the array looks like. Yeah, so now you can see the array. Here the array has 10 values along each dimension. Yeah, we have two-dimensional array, two opening brackets, and 10 float values along each dimension. But we can also have like 5 dimensions, and now the array will just, here we have squeezed text, and you can see, okay, we have basically 5 opening brackets, which means we have 5 dimensions, and then 10 values along the first axis, and so on. Yeah. So now this would be really a pain in the ass to define this explicitly. It would not even be possible, because basically, how many elements are in this array? Can you tell? Yeah, it's 10 times 10 times 10 times 10 times 10, so 100,000 elements. Yeah, you would need a lot of time just to specify this basic array. Okay, so this is kind of so therefore it's very important that you understand the shape property and how it works exactly, because you can use it to define arrays. And of course, you should also be able to define the d-type. I have not tried it, but let's try. So you have seen without the d-type, our array basically automatically converts to a float array. So you can see we have float values here. But what happens if we add the d-type? Yeah, then d-type integer, then we get an array of integer. Okay, so this is also possible to specify the d-type for the zeros function. What if we want to initialize with ones instead of zeros? Then we just use the ones function. Yeah. What if we want to initialize with 3 or 4? Say we want to initialize with 4, an array with values. Each value is an integer. Is integer 4. Then we simply use basic maths to achieve this. We initialize the ones array and we multiply it by 4. Yeah. So now we get our two-dimensional array with 10 values along each axis, and each value is basically equal to the value 4. Okay. So these are kind of the two most important. These are the two most important array creation routines. You will use them most often. Yeah, okay, so these are so with these two functions, the zeros and the ones function, you can create basic arrays. But how, for example, how can you create arrays that satisfy certain criteria? Say we want to have a one-dimensional array, like we had in the previous example, where we have values from 0 to 10. So like consecutive values from 0 to 10, 10 exclusive, so 10 not, maybe let's make 10 inclusive. So now we want to have this one. For example, for plotting, this is a very common case for plotting. We want to have equidistant values in this array. So how can we create this one? For this, you can use the NumPy arrange function. You define the start value, like we want to start our sequence with the value 0, and the stop value with which you want to stop your sequence. And in this case, we want to stop with 11 because the stop value is excluded in the sequence. If you would stop with 10, then it would just go up to the value 9. You can see it in a moment. And then you give this step size. So what is the difference between two subsequent values? So now let's print this. Let's print this array. Okay, and you can see that it gives you all the values from 0 to 9 inclusive, but we want to have from 0 to 10, so we add 1, and we get our resulting array, yeah? So the NumPy arrange function is very useful in many applications. Okay, so the NumPy function arrange creates a new NumPy array with evenly spaced numbers between start, which is inclusive, and stop, which is exclusive, with a given step size. Here we have the step size of 1. Good. Then, of course, I mean, with most array creation routines, you can specify the d-type, like we can have a float, say float 64, and now let's check. Okay, so now we have a float array. Good. Then the NumPy. So if you want to create an evenly spaced sequence of float values in a specific interval, the NumPy arrange function is not optimal because the documentation discourages this because it's improper handling of boundaries. So for in this case, so for example, if you want to have a sequence like from 0.5 to 9.5 with equidistant differences, and we want to have, say, 10 values in between, then we would use the NumPy linspace function. Yeah, so suppose we want to have this sequence, which I just copied, from 0.5 to 9.5. Yeah. Now, how can we get this? Basically, we would use the linspace function, where we have to give the start value. The start value is 0.5 and the stop value. And now the stop value is included. This is a special thing of the linspace function. So we include the stop value. And now we give the number of points that we want to have, basically. And now let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 values in between. Let's check whether I did everything correct. Yes, okay. So now we have 10 values in this interval. Yeah. So the linspace function is also very useful to create some basic one-dimensional arrays. And okay, so but what if you want to have this? Maybe we want to have this sequence. Like, let's copy. What if you want to create an with a scanning sequence of values, but in a two-dimensional space? For example, from 0 to 4, which is 5 values, and then from, say, 5 to 9, which is also 5 values. Okay, so now what if you want to have this two-dimensional array here? Yeah, so this should be the resulting array. Then of course we can create an array with ones or with zeros, and then modify the elements in this array, which we will see later. But this is not maybe the best way of creating NumPy arrays. It would be much better to still create a sequence here. So still we use arrange, and we don't want to have floating points, but integers. But now we reshape our array. So the reshape function allows us to give our array a different shape. Yeah. So and again we specify the shape, the resulting shape, with the tuple. And here we have two values along the first axis, which is each list is one value along the first axis, and each list contains of 5, or each dimension or axis consists of 5 elements itself. Good. Okay, so now if we print this one, then we should get our resulting two-dimensional array. Yeah, and you can see that we have from 0 to 4, and from 5 to 9 we have the two-dimensional resulting array. Okay, so this is really important, kind of, to get a feeling for this array creation routines, to use arrange, linspace, and reshape to and ones and zeros, of course, to these 5 functions to create the arrays you want, even multi-dimensional arrays, and to quickly get the resulting arrays that you want. So the next topic we are going to discuss is indexing and slicing in Python. Basically, now at this point we have already learned how NumPy arrays can be created, but most likely you won't know already if you are not already kind of familiar with NumPy how exactly you can access values in these arrays. Yeah, for example, I give you a very quick example about indexing. Here, now we have created this array A at this point. It's an array of ones. Now, what if we want to know a specific value of this array, like maybe the first value of this NumPy array? Now we can use, yeah, we have created this array of ones and multiplied by 4, and now we can access individual elements of this array via the bracket notation. We first have the opening bracket and then the closing bracket, and in between we have our indexing scheme. And now how exactly this works, I want to show you in this video. So basically in this part of the video series. Okay, so maybe first go back to the conceptual map. Okay, I don't want to have an infinite number of pages. Okay, now here we have an empty page. So first of all, NumPy indexing and slicing is very similar to Python indexing and slicing. I assume that you have already basic Python knowledge, but nevertheless, I will give you some basic idea how it works. Okay, say we have a string S with the characters universe. Okay, so we have these kind of 8 characters, and each character has an associated index position. Yeah, this is a 2, 3, 4, 5, 6, and 7. Okay, and now if we want to access, say, the 4th element of this string, we would just use print s, and now again we have this bracket notation 3, and within the bracket we use the index of this string element to return the character at this position. Yeah, so this is a position here, like we have this index. This index, and we use the index to access the string, and this works for any sequence. It works for strings, and it works for arrays, for lists, and for all sequence data types. Yeah, we have this basic indexing scheme starting with 0, not starting with 1. Therefore, an element with 8, therefore a sequence with 8 elements. The last element we would use 7 to access this. Okay. So now maybe let's have a practical code base to illustrate this. So we create a sequence of elements 1, 2, 3, 4, 5, 6, and then maybe make it 100 here. And now I give you some kind of only intuition how to access certain elements. If you access the second element, what would be the result of this puzzle? Yes, correctly, it would be 3. So let's check whether we are correct. Yes, because we have this element has index 0, index 1, index 2, and we are accessing the element from the sequence A with index 2, which is 3. Yeah, so we have the result is 3 here. Okay, what happens if we access element, I don't know how many elements are there. Okay, what happens if we access element 7? So element with index 7. Yes, correctly, it will be the 11. Okay, so now our result is 11. Okay, and now this basically the first element, let's make this crystal clear, has index 0. Yeah, the first element 1 has index 0. Okay, and now this is kind of the basis, and there is something some small detail which you should know, that we also can use negative indices to access elements. And if you use negative indices, we basically start from the last element. So the index -1 would refer to the last element. Let's check whether this is the case. Yes, 11. And then we go to the right, basically. Yeah, -4 would be the last, the second last, the third last, and the fourth last, which is 5. Okay, so this should be 5. Let's check. Yes. Okay. Now I hope you understood basic indexing. Now let's check slicing. How does slicing work, basically? Maybe we stay with no, maybe we have a string now, just to make it clear that slicing is works for both lists or strings. Okay, now the nice thing with slicing is that we can carve out whole subsequences of this string using kind of an advanced indexing notation, yeah? And the notation works like this. We have a start value and an end value, and yeah, we can then specify where to start our subsequence. Say we want to start at index 2 and end in index 5. And what does it mean is that basically the element at index 2 will be included in the subsequent, then all subsequent elements will be included as well until we reach the 5th element. And this element, so the index with index 5, which is the 6th element, and this element is actually not included in the subsequence. So think about this problem. What will be the result of this code snippet? So we start at index 2, which is the I, then we slice all the way to the right until we reach the element with index 5. So we have index 2, index 3, index 4, and this would be index 5, but it is not included, so I would be the result of this statement. Okay, let's check. Yeah, it's the result. Okay, so this is how slicing works, basic slicing in Python. And actually, slicing is a bit more powerful. It has a few more features which I will show you in a moment. So we can have also step size, like maybe make it 2. We start with element 1 and end in element maybe 6. And we only want to have every second element. Yeah, so this is an advanced slicing notation. We have like start. So we have x start, stop, and step. And so the third element, which is by default it is 1. The step size is 1. So it just which means that the step between subsequent indices, the difference between subsequent indices is 1, but we also can have individual or customized step size, which is 2 in this case. So what would be the result of this code snippet? Try to solve it on your own. Okay, so basically we start at index 1, so we kind of skip the first element. We start with the n. And then we only take every second element until we reach the 7th element, and this is not included. Okay, the 7th element is 4, 6, 7, this s, which is not included in the string. So the result would be n, v, and r. Yeah, so let's check whether this is the case. N, v, and r, yes. Okay. So this is kind of the advanced slicing notation. We can have the basic slicing notation only using start and stop, and we can have the advanced one using the step size as well. Now there are some few syntactic issues which I want to show you, which is the following. For example, we can have an empty start and empty step size, for example. In this case, we would use it would be equal to 1 here. I mean, if you have the empty start, this would mean that we start at the first element of the sequence included, obviously. If you have an empty step size, this would be the same as using step size 1. Okay, and we slice all the way to the sixth element, to the fifth element, and then we can have we can leave everything empty, obviously, which will be the whole sequence then. So everything will be kind of default. Then we can basically, this is a nice, it's still useful to do this because this basically creates a new string, the copy of the string. So if you want to quickly copy things, you can use this advanced notation. For string, it might not work because the Python interpreter, the Python runtime environment basically does not create a new string, but only points to the old string that is already created in memory. But for lists, this strategy would definitely work. Okay, so then we can have what else? So we can have a negative. This just looks like a smiley face, but it's not a smiley. It's basically negative index, which means that we slice all the way to the end, but remove it, but not including the last index. Yeah, of course we have to define the variable on which we slice. Okay. So we have universe, but without the e at the end. Then we can have, this is also interesting. We can use default values for the start and stop value, and then have a negative step size. Negative step size means that we start from the right and slice to the left. Okay, so in this case we have universe from right to left, so we slice backwards. We also can have slice only every second element. Okay, then we skip the u, we skip the I, and so on. Okay, so I hope you understood slicing, basic slicing in Python. Obviously this is not a Python tutorial, but I still wanted to include this here because NumPy really is very much based on the Python slicing notation. So if you understand Python slicing, then you will also understand NumPy slicing as well. So in NumPy, we have to differentiate between one-dimensional arrays and multi-dimensional arrays because slicing works differently for both arrays. So let's start with one-dimensional NumPy arrays. And they are basically similar to numerical lists in Python, so you can use slicing in NumPy as you use slicing for lists, as we discussed in the previous video. So maybe the best way of showing it to you is to create a sequence of examples, and then I just explain the slicing concept by example to you. Okay, so first we create an array A, use the arrange function again to create an array like this. Okay, so we print the array. Yeah, we have an array from 0 to 9, from start to stop excluded, and now we use different slicing methods to access the array. Okay, so first we print A. Now we do this one. Basically for 1D slicing. So all examples I use now are basically for 1D slicing. Later we will have a look at 2D slicing, or maybe even more generalized XD, so multi-dimensional slicing. Okay, so if we are doing this, we are basically creating a copy. Yeah, so we are using slicing to create a copy of the array. So and this should result in exactly the same elements here. Okay, so now what happens if we are using this notation? Yeah, you already know the first element before the colon is the start index, and the element after the colon is the end index. We don't have any step size here, but we can also use step size, as you will see in a moment. Okay, so now what would be the result? Yes, it will be the list starting from 1. Yeah, so we skip the first element basically. Okay, now again, what happens if we are using, say, this one? If you're doing this one, like from 1 to 3, maybe. Okay, then you see we start with the element with index 1, which is this one, and end in the second, in the element with index 2. 3 is not included, as you know, yeah? So the index 3 is not included in the slice. So we have a slice with length 2. Okay, now again, we can have something like using only every second element. So now we specify the step size, and the step size is 2. So the difference between two subsequent indices which we access is 2. Yeah, so we access, for example, the first element, then the third element, then the fifth element, and so on. Yeah. Okay, now what is the result here? Yeah, we have only the even values of the sequence, which makes sense. Yeah, you will need this very often in practice. Yeah, so try to understand it properly. Okay, then we can have of course we can also specify a start value like this. Then we would have all the odd values. So now we accessed the even values, then the odd values by starting with the first element, and then we can slice. Maybe we can do this one. This is interesting. This is an interesting example because now we have negative slicing. We only access every second element, every other element basically, and our end index is 1. But at the start index in this case is the last sequence element because we start on the right, not on the left. We start not with the first element, but we start with the right, with the last element. And now we slice all the way up to the first element, excluded. So we don't have the 1 in our output. Okay, let's check. Yeah, we have the sequence backwards from 9, 7, 5, 3, but 1 is not included in the sequence. Okay, so this is very interesting example. We can have even more complex one, like starting with -1 and going all the way to 1, and yeah, again we have every other element. And now what would be the output here? Exactly the same. Yeah, so we have because in this case, if we have negative step size, our default element is -1 because we start -1 indices is the index of the last sequence element. So if we are writing -1 as the start index, we are basically doing exactly the same as the default slicing behavior. Okay, so now from these examples you should see that one-dimensional slicing is basically exactly the same as multidimensional slicing. Okay, but in contrast to regular slicing, NumPy is a bit more powerful. So now we can have, I will show you another example, how NumPy handles the assignment of value to an extended slice. Yeah, so we have basically how it's more about slice assignment. Yeah, so now actually I have not introduced slice assignment to this up to this point. So now let's going back to Python. Yeah, slice assignment in Python. Now this is a very useful feature to know. So this is, say we have a list with values 1, 2, 3, 4, 5, 6, and now we want to replace every second element with the value 4, for example. Yeah? No, so let's say with the value -1. So we have -1, -1, and -1. Okay, because we have 6 elements, we can select the slice on the left-hand side of the equation. So previously it was kind of on the right-hand side, which is just a return value. But now this means that we select some elements of the list which we want to replace. And we want to replace them with this list. And the list should have exactly the same shape, so to say, than the original list. And now we can print L. And you can see that, yeah, we have this value -1, which has replaced some values of our list. But now the problem is with traditional slicing that we cannot use this notation here. If we are doing this one, then of course it will throw an error, because here on the left hand side of the equation we select a subset of list elements basically that has length 3. So we select 3 elements, but we try to replace 3 elements with by a single element. I mean, conceptually it's clear what we want to do. We want to replace all the elements that are selected here by our simply by our integer, which we give on the right hand side, but Python will basically throw an error. Yeah, so we must assign iterable to an extended slice. This is the extended slice, and we want to assign this iterable. And of course, an integer is not iterable, so it throws an error. But basically, if we would do the same thing in NumPy, this would work. So say we create a NumPy array. 1, 2, 3, 4, 5, 6. And now first we do this. And now we have the same here. Okay. Now you can see everything works properly. It does exactly the same thing as we actually we want to achieve, as we did previously, but without requiring us to specify a sequence that we assign. The reason is that broadcasting in NumPy, which we will look into at a later point in time in this tutorial. Okay, broadcasting means it automatically, kind of, if you have an operation and the operation requires 2 arrays to have the same shape, then NumPy tries its best to bring these operands into the same shape, basically. And here it sees, okay, now we have a NumPy array. We have selected NumPy array on the left-hand side, but on the right-hand side, we don't have a NumPy array yet. So NumPy just creates a NumPy array for us. This is a kind of a very fine granular, very it's a good piece to know, but maybe it's not. I think in practice it will occur, basically. Yeah. Okay, so this is everything I want to discuss for one-dimensional slicing in NumPy. Let's move on to x-dimensional slicing. Yeah, so NumPy, basically the big advantage of NumPy is that it easily allows to access and modify and convert multi-dimensional multi-dimensional arrays. So this would be in Python using lists for this kind of linear algebra operations would be a pain in the ass. Okay. So first, multi-dimensional slicing operations consist of multiple one-dimensional slicing definitions. Yeah, so very simple. So if we defined like say we create a NumPy array with 2 dimensions, 1, 2. Let's make it. So we have the arrange function. We use 1. We start with 0 and in 9 and yes, and then we reshape it. 3 at the shape tuple 3, 3. So we have 3 elements in each dimension. And now we print x. Now we should have a 2-dimensional array here. I just remove everything above, yeah, but it doesn't confuse us. Okay, so now we have this 2-dimensional array, and now how to use slicing for this array, basically. And the simple idea is that we can use our start, stop, step notation along each dimension separated with commas. Yeah, so we have stop, step. Okay, now we have this opening bracket notation, and then we have the slicing, which we already know from the one-dimensional case, but now in the multi-dimensional case, we just have multiple such slices, and we separate them with commas. And of course, if we have a higher dimensionality, like 10-dimensional space, then we would have 10 such notations. Yeah, and okay, and as a general rule, slice each dimension independently by separating the slicing definitions with a comma. And within each dimension we use the colon notation. Of course, we can again skip the step definition also. We can also skip some columns, as you will see in a moment. Okay, so now we have the array, and now suppose we want to say slice all the rows. In two-dimensional case, the first axis are the rows and the second axis are the columns, and we want to slice all the rows, which means we use the default slicing notation, but only say we want to only use the first column. Actually the second column, but the column with index 1. Yeah. So what would be the, again, so I just give you the output here. So what would be the result of this slice notation? If we print x, we slice over all rows, and then we print the second column. Okay, let's check. Yeah, it will be 147, because we have here the second column is 147. Yes, this is the output of our slice. Okay, this basically means we fix. So this is basic indexing. This is not slicing on the right hand side. If you don't have the column notation, of course we are using indexing, but we can also use the column notation, like we want to slice all columns starting from the first column, which means skip, basically starting from the second column, we skip the first column and ending in the last column. Yeah. So in this case, what would be the output? It will still be a two-dimensional array, because our output is, we still have this column 147, and we have the column 258. Okay, so but we have only skipped the first column. Okay, now say we want to use all columns but all rows but the first one. Yeah? In this case, we would have a quadratic array again, because we just basically we have the 7, 8, 7, 8, and 4, 5, 4, 5, because we skip the first row and the first column. Yeah. Okay, so it's very similar to one-dimensional slicing, but we have this comma-separated list. And maybe I just give you a few more examples so that you really nail this down. What happens here if we use this notation? What happens? Yeah, we slice all the rows and we slice all the columns, but not the last column. So basically we cut the last column and throw it away. This would be the result. Let's check. Yeah, our result is here. We have, this is original array, and this is our array here, which consists of the first and the second column, but not the last column. Okay, and then again, otherwise I don't think, maybe we can even have this interesting example. Let's just remove this slice here. Okay, so here, what would be the result of this slice notation? In this case, we use all rows and all columns, but skip every other column. Okay, so in this case, we would use the first column, skip the second column, and then take the third column again. Yeah. Okay, as you can see, slicing multidimensional NumPy arrays is very similar to slicing one-dimensional array. The most important information to remember is that you can slice each axis separately. Okay. Okay, there's one piece of information that is also quite interesting, which I want to show you, which is the following notation. So say we have this array X, and now first I have to create a very high dimensional array. So say I create an array like A equals NP arrange, like 27 values, and we reshape our array to have 3 dimensions. So this is now a 3-dimensional array. Yeah? We have 3 elements in each dimension, so we have 3 times 3 times 3 elements in our array, so 27 elements. And now if we print A, we get the following result. Yeah, we have a 3-dimensional array. Let's remove this one. And now what we can do is the following. We can again, we have this, now we have 3 dimensions, which means that we have 2 commas, and now we can use slicing for each dimension separately. But we can also, if we don't want to, we can basically give this dot 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 notation. This is a very special feature, and many people won't know it, and they will look very confused if you use this coding technique. But it's advanced, it's fun, and it's easily understandable. Yeah. So you want to, here this means we want to have in axis 0 we want to have only the first element, and for axis 2 we only want to have the first element, but we want to use all the remaining elements. Yeah. So if we print this one, yeah, so we have then yeah, for axis 0 we only want to have the first element, which is this matrix is the first element of axis 0. Then for axis 2 we want to have all elements, which means all columns, this, and this. But then within each of them, basically we want to have only the first element, which is here 0, 3, and 6. Yeah, so this is the result, 0, 0, 3, and 6. So this is kind of, it's really difficult to grasp in your brain, to visualize the array and then grasp what happens here. But it's also very important, and I think I gave a very slow introduction into this topic in this video, and I hope that you by now have understood how shape and reshape works, how the different axes works in NumPy. And yeah, if not, maybe I can quickly okay, now this is broken, this doesn't work anymore. Okay, or yeah. Start drawing. Okay, now again, if we have only a one-dimensional array, then this would be our axis 0. If you have a two-dimensional array, then this is our axis 0, and this is our axis 1. Yeah. So axis 0 is the rows, and axis 1 is the column. If you have a three-dimensional NumPy array, then of course now it depends, because the cube can have different axes, but now we have here axis 0, axis 1, and axis 2, like this, yeah, and so on. So we have every kind of dimension has its own axis identifier, and we start from outermost. So if we define the arrays, we have this bracket notation. Just think of the NumPy arrays as lists of lists, yeah, for example like this. And then we have some follow-up things. We have 3 opening brackets, which means we have 3 axes. This one, so this whole thing, say it closes here, this whole thing is basically axis, is the first element of axis 0. Yeah, and then if we move into this, then you see, okay, this one is the first element of axis 1. And now if we even have some values here, like 3, 2, and 1, then this element is the first element of axis 2. Okay, so we just count the opening brackets and check the first element to see what is the first element of the axis. Good. Okay, I hope that this made sense for you. Maybe. So what else? Maybe there's one interesting accessing scheme which I want to show you in NumPy. This is also very special to NumPy, but extremely important. Yeah, you should really now be giving me your full attention, because this is a very important feature which will be used later very often. Okay, so suppose we have this NumPy array here, the two-dimensional array, 5 and 8. Okay, and it closes. If you print the array, it looks like this. We already have seen this array a lot of times, and now we can use special indexing scheme. We can use an indexing array. Let's call it indexing array, so that you understand that it's an index. And it has exactly the same shape. Yeah? And in this indexing array, I just give the Boolean values. Let's just specify Boolean array. So it has exactly the same shape as our like data array, but for each index we basically give a truth value, whether we want to include this index or not. Okay, and this means that we can have very specific indexing schemes, like here. Like we access the first element in the first row, so the first column in the first row. Basically, we access the whole first column, but then we access no element of the second column and only the second element of the third column. Okay, and now we can use this within our bracket notation. So it's really powerful. This bracket notation is really powerful in NumPy. We use our indexing array to index specific elements. But of course, as we now the array would not be homogeneous array in terms of the data we put in, because now we access like the first column, but only one element of the third column and not the second column, which means that the array would look very skewed. Yeah, it would be like it would be an array like this. We have some value here, some value here, some value here in the first column, and this we wouldn't have. We only would have this value. Yeah. So this is not a NumPy array. It doesn't have the shape of a NumPy array, so this would not be allowed. Therefore, NumPy, if you do this, the result wouldn't be a two-dimensional array. It will always be a one-dimensional array. Yeah. So if you print this, if you use the indexing array, then it will always convert the result to a one-dimensional array, and we would include only the elements that have a true value associated to them. Okay, which means the elements 0, 3, 6, and 5. Okay, let's check. Yeah, we have 0, 3, 5, and 6. We have all these elements. Okay, so we have the flattened array basically. This is a very powerful and beautiful indexing scheme, isn't it? Good. So this was everything I want to tell you about slicing in NumPy. I think these are really basic and important fundamentals that I've taught you here in this video up till now. I tried to be very slow in the progress and to explain everything that came to my mind, so that you get everything until now. Even if it seems to be slow progress for you or for some people who are listening to this video, I think it's good to take time once, to invest this time once, because it will pay back 100-fold later in your career if you use NumPy. You should have kind of one time somebody should have guided you through the thought process and to the different features and tricks with NumPy, and I hope I could provide you this. Okay, next I will quickly give you kind of an overview of different functions. I just want to go over a cheat sheet that I have prepared, and which you could also download. I give a link in the description below. NumPy cheat sheet with the most important NumPy functions, and then I will give you some code puzzles that are also in the book. So basically, all the examples I have used up to this point are based on our book Coffee Break NumPy, which is a comprehensive NumPy compendium, which will lead you kind of practically in small doses or small bits of information towards NumPy mastery, and it's based on puzzle-based learning. So puzzle-based learning is a very engaging technique to make you retain your information. So you first you create a puzzle. I ask you a puzzle, for example, and then you have to think about the solution before I give you the answer. And by thinking about the solution, you open a knowledge gap. You become aware, and your subconscious mind becomes aware that you don't know the information yet. So at the point when I give you the information, you will be prepared to absorb the information and to fully grasp it and retain it also. So it's a very efficient technique. It's based on scientific studies in the area of educational science, and it has been shown that it can improve retention by 44% or more. So if you are interested in this type of learning, on this learning technique, then definitely check out my book Coffee Break NumPy. It's available for a few bucks, and it can provide you thousands and thousands of dollars if you decide to start your kind of freelancing business or your career as a data scientist. In the book, I have also included a Python cheat sheet, a NumPy cheat sheet, which gives you the most important NumPy information. It's like a quick rush through all the NumPy functionality, and here the cheat sheet looks like this. So we have this NumPy cheat sheet, we have the shape. You can, by the way, you can also download this cheat sheet as a PDF from a website. I will give a link in the description below. And basically it gives you the most important information there is about NumPy. So maybe the 17, I think it does. I think 17 most important functions, yeah, which you can use. And I will quickly rush through the functions before we dive into the puzzles, so that you already have an initial overview. You don't have to understand all the functions now at this point. I just give it to you. It's kind of an initial tutorial, and later we will dive into some functions more. But also you will be able to understand how the functions work more closely. Okay, so let's start. So first let's start with something that you have already seen. So now first we create an array. The array has maybe 3 dimensions. So we have 1, 2, 1, 1, and 0, 0, like this. And yeah, it's a 2-dimensional array with 3 elements along the axis 0 and 2 elements along axis 1. And now we can print the shape of this. The shape you have already seen. The shape is a tuple. Each tuple value indicates the number of elements of the respective axis. So we have 2 axes here, 2 tuple elements, 2 dimensions, and 3 elements in the first axis, 2 elements in the second axis. So this you should already know by now. Then we have the ndim property, which I have also shown you. I think this was one of the first things I showed you in this video. And we have 2 dimensions, so the ndim property returns 2. Then I will show you our first matrix multiplication operator. Yeah, we have this. Let's say we have this array, and we have another array which has exactly the same shape, almost the same shape. 1, 2, 3, and should this work? Yes, this should work. 1, 1, 1. So basically I can draw it for you like this. We have 2 arrays. The first array is 1, 2. So let's move here. We have 2 arrays. Okay, so the array A, we want to multiply array A with array B. Okay, and A has the following shape. We have 3 rows and 2 columns. So we have, it's like this. And B has the following shape. We have 2 columns and 3 rows. And here we have 1, 2, 1, 1, 0, 0. Like here, 1, 2, 1, 1, 0, 0. And 1, 2, 3, 1, 1, 1. 1, 2, 3, 1, 1, 1. Yeah, like this. And this is our matrix multiplication, which we want to achieve basically. Now this is what we want to achieve. Now you will be surprised, because if we are simply writing now intuitively, if you want to multiply these matrices, then you would expect that this will be the matrix multiplication operator. Yeah, after all, it's a multiplication operator. So if you have 2 NumPy arrays, A and B, and you use the multiplication operator in between, then you would expect that you by default it performs matrix multiplication. Okay, so let's check what would be the result basically. I'm not going to calculate this in my head, but you can see maybe we calculate the first element. So we have 1 multiplied with 1 is 1, plus 2 multiplied by 1 is 2. So we have 1 plus 2 is 3. So the first element should be 3. Now let's check whether this is the case. Okay, no, there's an error, and the reason is that the star operator does not perform matrix multiplication. In fact, the star operator basically performs element-wise multiplication of the elements. Yeah, so this is a kind of a common mistake. If you want to calculate the matrix multiplication, then you would use the matmul operator and use the two matrices as the operands or the parameters to the matmul operator. And in this case, we would get our resulting 3 times 3 array with the first element being 3. Yeah, so we have here we have 3 elements, 3 rows and 3 columns, and we have a 3 times 3 resulting array. So this is exactly what we would have expected. Okay, so then we know the matmul operator, but what's the star operator? What does this operator do basically? And in NumPy, maybe this is a general general hint for you, that in NumPy, if you don't have any clue about the semantics of an operator, then you should first assume that it's element-wise operation. Yeah, if you have 2 operands and you glue them together with plus, with minus, or with anything, then or with multiplication even, then you have this element-wise operation. So this means that, say we are say we have this 2-dimensional matrices which have the same shape, and this was the problem previously, that we wanted to kind of combine these 2 matrices. So let's make it 1 0 0 1. Okay, that we want to combine these matrices that had different shape, but now they have the same shape. So now we can perform element-wise computation. Yeah, as you can see, we have 1 2 1 1. This was the first matrix, and now we multiply element-wise, which means we have 1 times 1, 2 times 0, 1 times 0, 1 times 1. So result is 1 0 0 1, obviously. Okay, so now we have the element-wise computation. This operator is not matrix multiplication, as you know it's the element-wise multiplication. And also the plus, equally, it's element-wise operand. Yeah, we have 1 plus 1 is 2, so the first element is 2. Also minus works like this, so we can use basic basic arithmetic operations on the matrices, but then they are element-wise operations. So for the advanced operations, we should use the matmul, for example, or the functionality. Okay, then you have already seen the arrange function. So I will maybe linspace and arrange I will skip for this. These are important functions. Or maybe let's make it a bit repetition is not too bad. So we have the arrange operator, arrange method, and it takes a start, stop, and step size. You can also only use stop, then it will start with 0 and step size of 1. And if you print A, then you see it's a 1-dimensional array of subsequent elements. And we can also have redefine A with a linspace operator. It uses start, stop, and number of points. So start, maybe we start, so we have to specify the interval. Maybe let's start with -10 and we stop with 10, and we want to have 21 values. And now we can decide whether we want to include the endpoint or not. Endpoint is by default included, as you know, but now let's exclude the endpoint specifically. So 10, the value 10 will not be in the final sequence. Let's print the array. Okay, I move it up so that you can see it as well. Okay, so now we start with -10, but we don't stop with 10. 10 is not included in our interval, because we have specified the endpoint false. If we want to include it, then we can specify endpoint equals true, but this is also the default value, so then in this case we would include the value 10 to the sequence. Okay, this is linspace, how we can create array. Then let's move on to a bit advanced functions. So we have this array again. Say we have the original array, and now we can calculate the average. So print NumPy average of array A. Yeah, so what would be the average? The average is 1.25 because it's a numerical value, because it just goes over all values. It sums the values in the array, like 1 plus 2 plus 1 plus 1 is equal to 5, and then it divides by the number of elements, is divided by 4, so 5 divided by 4 is 1.25. So this is a result of this operation. But now we can have the same for variance. Then we have variance is also over all, or the var operator, sorry. Variance is also a statistical measure. It basically calculates this squared standard deviation, and standard deviation is the kind of average deviation of the values from the mean in the array. So it first calculates the average, which was 1.25, and then it checks, okay, 1.25 minus 1 is 0.25, 1.25 minus 2, and so on. Yeah, so it checks the distance between these values. So distance between 2 and 1.25 is 0.75, and here 0.25 and 0.25, and then it calculates the average of this, which is standard deviation, and the squared standard deviation is the variance. Okay, and of course we can also use standard deviation. So the deviation is, yes, it was standard deviation. I'm always confused whether it's def, NumPy def, or NumPy std, but it's NumPy standard deviation. Okay, and we have standard deviation. So, and basically, just to check, this one should be, so if we square this value, it should result in 1.825. So let's check whether this is actually the case. So we have this one squared is approximately, yes, 1.875. Okay, so we have standard deviation, variance, and okay, these were some important metrics. But now let's go back to the average, because I wanted to show you something. So the average, standard deviation, and variance, they kind of aggregate the values of an n-dimensional NumPy array into a single value. But what if you want to calculate the variance along a certain axis, like for example, we want to calculate the average value of this axis 1 and the average value of this axis. So how can we actually achieve this? And the answer is by specifying the axis keyword. And this is very important. Many NumPy functions allow you to specify the axis keyword, which means that you are performing this operation along a certain axis. So for example, if you collapse or aggregate statistics over the whole array, and now you specify the axis argument, then it won't aggregate it over the whole array, but only along the axis. So it would collapse basically axis 0 to a single element, or axis 1 to a single element. And we wanted to specify, we wanted to collapse axis 1, which is, we have two opening brackets. So this is basically, these two elements are in direction of axis 1, and we want to collapse them into a single value. So then we should get 1.5 and 1.0. It will be a float array. So let's check what happens. Yeah, we have 1.5 and 1.0. The 0 is often skipped for floating point numbers, as you know. Okay, so it's just a way of writing things here. Okay, so this is a very interesting feature, yeah, and it works for everything. It works for variance, and it works for standard deviation. Yeah, it works for all these operations to collapse not all values into a single value, but only the values along a certain axis. And of course, we can also do this along the first axis, so axis 0. Yeah, in this case, we maybe in the average, you can more easily compute the average in your head. Okay, so now we want to do this along the, so let's write it like this one. So first we have collapsed these two elements together, but now we want to collapse all the columns together. That's why we specify x is 0, because it means we still want to have the columns in our resulting array, but we want to collapse the rows together. And we specify the rows by giving the axis 0, because here the rows are along axis 0. Which means, yeah, in this case we have 1 plus 1 divided by 2 is 1.0 and 1.5 again. So this would be the result, 1.0 and 1.5 again. Okay, so these were now we have covered a very important subset of functionality in NumPy, and also how to use the axis argument. This is very important for later puzzles, and also later practical application. Good. Then what you have also seen is kind of this replacing. So let's say we have an array with 10 values. Print the array, and now we want to replace some values, like every second value we replace with -1. We have already seen this, but I just want to show you that it works. And now we print a array. Okay, and now you see every second element is replaced with the dummy value -1. Okay, this is a very useful feature of slice assignment. I write it like this, that you see it's slice assignment. When people talk about this, they usually refer to it as slice assignment. Okay, then another interesting NumPy function is the diff function. You will see this function in practice a lot. Basically, if you calculate the diff function, then it will. I show you, and I try to figure out what it does actually. Okay, now we shouldn't use slice assignment here. Okay, now again. Okay, we have created this array of subsequent values, and now what exactly does the diff function do? Yes, it calculates the difference between two subsequent values. Yeah, so we have like 1 minus 0, 2 minus 1, 3 minus 2, 4 minus 3, and so on. Yeah. So let's say we calculate the diff of the reverse sequence. What will be the output? Exactly, it will be a sequence of -1s. Okay, and then we also have we can do the following. We can calculate the diff and the diff of a diff function. So what does this do basically? So now we have the original array, we calculate the diff, which was an array of 1s, and now we calculate the diff again. Then it will be an array of 0s, yeah? So if you execute this, you will see it's an array of 0s, because so calculating the first level difference is an array of 1s, and now we calculate the second level difference, which is 1 minus 1 is 0. For every element, it's 0. But there's also an easier way of writing this. So we calculate, we can specify the value like 2 here. The default n value is 1, which means it calculates the first order of difference. But we can also calculate the second order of differences like this. And then you see it's exactly the same output. Okay, so this was the diff function. It's a very useful function, a small little trick. Then we can have the CumSum function, CumSum of the array, and also of course the diff function and the CumSum functions. Can I show you? NP CumSum also allow you to specify the axis parameter. So you can do exactly the same thing. You can use a multidimensional array and then perform an operation only along one axis. Yeah, but we are not going to do this here because we have already covered it for average and standard deviation. But it's really, this is one of the most important conceptual things you can learn in NumPy: how to properly use the axis parameter to get your code executed. Okay. So we have the CumSum operation. CumSum is short for cumulated sum. So we have this array of like 1, 2, 3, 4, 5, and now the cumulated sum is the sum of all values until we reach this index of the element. Okay, so we have like here the sum 0, the cumulative sum is 0, but for the first element the cumulative sum is 0 plus 1 is 1. Here we have 0 plus 1 plus 2 is 3. 0 plus 1 plus 2 plus 3 is 6. 0 plus 1 plus 2 plus 3 plus 4 is 10, and so on. Yeah. So this is kind of the you know, this story about Newton, who calculated this in his head as a 9-year-old student. Within seconds, he calculated the cum sum of all values and from the first of all the 101st values. Okay, nowadays, yeah, you can easily see, okay, the cum sum of all the values from 0 to 100 is 5,550. So nowadays, the smart kid would not calculate it in his head, but use the NumPy cum sum operation. Okay, then we have a few interesting functions as well, like the sort function. So for example, say we create a manual NumPy array. So first maybe create an array of some, maybe manually create an array of some values like this, and then we print NumPy sort A. So what happens? Of course, we sort the array in ascending manner. So the first element is the smallest element, the last element is the largest element, and all the elements in between are sorted as well. Okay, so this is kind of it's an important application. So sorting is obviously it comes very often in practice, but also what comes often is the following. Like suppose we have an array of customers like Alice, Bob, Carl, Pete. Yeah, like this, we have 4 customers, and then we have an array of value, like how much they have already bought from our company, for example. Yeah, so maybe Alice has bought a product costing $1,000, $500, $800, and $900. So this means Alice has bought a product for $1,000, Bob has bought a product for $500, Carl has bought a product for $800, and Pete for $900. And now, if we simply sort the value, then we have lost our relation to we have lost basically our ordering. Yeah, that we know. Okay, the cheapest customer has a value of 500, and our best customer has a value of 1,000. But it does not tell us who is our best customer, basically. And for this kind of problem, we need the argsort method, because argsort does not give us the sorted sequence, but the indices of the sorted sequence. In this case, it means we first have 1, so the second element, Bob. Bob is our first element in our arg-sorted sequence. Carl is the next element with 800. Pete is the next element with $900, and Alice is the last element with $1,000. Okay, now we have the sorted indices, so the indices that would sort the sequence basically. And now we can use this sequence to access our customers in a sorted way. Yeah, so we have our customers, which is a list. We use the indexing method, this opening bracket, and we put in a sequence of indices, and the order of these indices determine the order of our resulting output. And now you can see an arrow. So what happens here is print customers argsort way. Only integer scalar arrays can be converted to a scalar index. Okay, what does it mean? Maybe we have to create a NumPy array here out of this. Okay, yes, this was a problem. Okay, so now you see we are sorted by customer value. Bob has the smallest customer value and Alice has the largest customer value of 1000. Okay, so now we have used the argsort method to return us the indices of our customers or of our values, and we use it to access the customer names as well. Okay, so this is an important application. Argsort gives us the way of reusing the information for other arrays that are sorted, that are related to our array to be sorted. Yeah, so we want to sort according to the value of our customers, but we want to have the names of the customers. This is important information. Okay, then we can do the same for we can use the max function, which is our so what is the maximum value, for example? Our maximum value is 1000. This doesn't help us in this case, therefore we want to use the argmax. Argmax gives us the index of the person with the maximum value, which is 0, which is Alice. Yeah. So there now we can print customers. Now we can again print our customers and use the argmax, the maximum value, the index of the maximum value, and then we get the result. Alice is our customer with the maximum value. And of course we can also use argmin, which is Bob. Okay. Then one thing I want to show you is the non-zero operation. Non-zero is an important operation for finding elements that meet a certain criteria. Yeah. So basically, say we have an array. Say we have an array B. So let's create a new array, NumPy array 1, 2, 0, 0, 0, 0, and 3 and 0, like this. And now we print non-zero, and the result is the indices of all elements that are not 0. Yeah, so we have A, 1, and 6. So these two elements and this element have values that are not 0, basically. Okay, and this can be used to find certain elements. Yeah, like if we use, for example, give me all elements that are non-zero, then we would maybe let's skip this last example because it comes later in the puzzle and I don't want to give you the puzzle already. Okay, so this is the basic information that is provided in the cheat sheet. I quickly rushed over all the most important functions. I think these 17 functions are at the core of NumPy. You will use them very often, maybe 80% or 70% of your time. If you're coding, you will use these functions, maybe even 100% of times, because you always have to create arrays and you have to access them, and you calculate like averages and use arrange to create new arrays, use diff, variance, use the axis argument. These things are really basic. Use shape, for example, or the number of reshaping, the number of axis, and so on. Okay, these are really critical values, and I hope that by now you have critical functions in NumPy, and I hope that by now you have understood everything to this point. And now we will move on with a bit more fun. I will give some puzzles. I will give you some puzzles, then you have to guess the solution, and I will explain it to you. I won't give you all puzzles because you should also have a reason to buy the book, in which all these functions and puzzles are explained in a very detailed and concise manner, again, so that you can start your data science career and start earning some money with NumPy. And of course, learn NumPy the fun way and an efficient way, because I want that your time is invested properly in a positive return on invested time manner. Okay, so in the remaining part of this very long NumPy tutorial, I want to provide you the opportunity to practice what you have learned and to improve your skills by solving Python puzzles with me. And I'm using puzzles from the book, from the Coffee Break NumPy book. Again, link in the description below. It only costs a few bucks, but provides you thousands of dollars of value if you are really, because it can really help you to improve your skills. And one thing that comes with the book is all the puzzles in the book as a Jupyter notebook. And this is how I will now quickly go over some puzzles, not all of them, so that you still have something to do if you buy the book. But yeah, so it will be, I will just go over the puzzles, solve them for you, and tell them and explain it to you. So okay, at the heart of the NumPy library are NumPy arrays. And we have already looked into multiple ways of creating arrays using the NumPy array function. And yeah, we simply here in this puzzle we create an array called NP array, and it has the values 1, 7, 2, 3, 1. And first we print the length of the array, which is, of course, we have 5 elements, so the length is 5. Then we print the size. The size basically shows us, in this case, of course, the array has also size 5. It shows us a number of elements. So it's a property of the array. It's a number of elements. And you will see later that there's a difference between those two, between the length function and the size object, the size property of the NumPy arrays. And then the max function, of course, it returns the maximum value of the array. So we have 5, 5, and 7. Let's check whether this is the output. Yes, it's the output. Okay, so let's move on to a two-dimensional array. Here, the NumPy 2D array creation. Can you solve this puzzle? I will give you a few moments. Okay, again, we have a two-dimensional array with 2 rows and 4 columns, and we create a variable NP array, and then we print the length, the size property, and the maximum element. Okay, again, the maximum element is easy. We are not calculating the max along a certain axis or something. It's just the maximum elements among all elements. So here the maximum elements is 5. So the result here is 5. Then the number of elements in this array is obviously 8. And you would also expect that the length of this array is 8, but actually it's not the case. And here you first see the difference between the length function and the size property. The length function basically returns 2 in this case, because the outer NumPy array, you can say the outer list, has only 2 elements, which are the 2 inner lists, or the 2 rows. So basically this gives us a number of rows in this case, and this gives us a number of elements, all the elements put together. So we have, the result is 2, 8, and 5. So let's check whether this is correct. 2, 8, and 5 is correct. Okay, so move on. And the puzzles are getting harder and harder along the book. So of course we start with simple puzzles, and then the puzzles are becoming harder. And now in this case, some pieces of knowledge are nice to know, but optional in NumPy, but the endim property is definitely not one of them. And we have already introduced the endim property 2 times. And in this case, yeah, this is all about the endim property, this puzzle. So every puzzle, a good puzzle, delivers one piece of knowledge and really hammers this piece of knowledge into your brain so that you don't forget it in the future. Also in a year from now, you're able to recover the knowledge that you have learned. Good. So in this case, we have 4 lists basically. Here some salary data in $1,000. So for example, in 2015, the data scientist earns $133, and the product manager earns $127, and so on. And now we create a new NumPy array. It's a 2-dimensional array using these lists as input. And now we print the number of dimensions. And of course, as I already told you, the number of dimensions is 2. We have a list of lists, or 2 opening brackets. They are kind of implicit, and this is the difficulty of the puzzles, because we are using this variable instead of putting the list directly into it. So it's very basic, it's very simple, but as I told you, the puzzles are becoming harder and harder. Okay, so let's run this. Okay, you can see the result is 2. Okay, move on to the next. Now we want to access the array shape. And the basic building block of your proficient NumPy education is the shape of a NumPy array. And so a multitude of NumPy functions allow you to explicitly specify the shape object and provide a different semantics for you depending on your choice. Okay, so we have again this same data set as before, the salary data for 3 years. And we create the same array as before, and now instead of the ending property, we print the shape. Okay, so think about this. What is the output of this code? Yes, so we have the first element of the shape object is, so basically the shape object is the shape tuple gives us for every axis the number of elements in this axis. So okay, we have the first axis is the number of rows. So we have 4 rows and we have 3 elements in each row. So 4 and 3 would be the output of this puzzle. Okay, which is also correct. Good, let's zoom a bit out. Okay, then the next puzzle. It's kind of a puzzle rush, but I think, so if you want to really dive into these puzzles and understand everything and get the step-by-step explanation, then you should definitely get the book. Otherwise, I would just rush over the puzzles. Again, now we have some price data. So in general, rows, columns, shape, and reshape. This puzzle is all about strengthening, and I'm quoting from the book now, strengthening your understanding so that you can grasp the meaning of NumPy code fast. Okay. So here in this case, we have this price array, which is a one-dimensional NumPy array, and yeah, basically we create the array here, prices. Then we reshape the array. Okay, this is now we make. Basically, you have not seen this notation. You have only seen the notation with another, with an explicit tuple here. Yeah, but in this case, it's also possible for reshape to kind of give the tuple implicitly. Yeah, so we have the number of rows and the number of columns. So the number of elements along axis 0 and the number of elements along axis 1. And here it tells you that later we have 4 rows and 3 columns. Yeah. So basically, and now we print the average. The average of the first element. The first element is kind of a trick question, because here we have 4 rows, but here in the prices array we indicate that we have only 3 rows. Yeah, so it tries to trick you into thinking that the array looks like this formatting, but actually it doesn't. Yeah, so we have these 3 elements are in the first row. Okay, and now we calculate the average of the first element, which is this one, which I have just marked. And the average is, so we have 9, 6, and 6. So 6 plus 6 is 12, plus 9 is 21, divided by 3 is 7. So the first output is 187. And we convert it to an integer, so the result will be integer as well. Okay, and then we use the last element. So the last element consists of these 3. The last row here, -1. The last row of this 2-dimensional array consists of these 3 values. And again, we have the average is obviously 187 because we have 188, 186, and 187. Okay, so if you add them up and divide by 3, we get 187. We convert it to an integer, so we have 2 times 187 as a result. Let's run this and check whether this is correct. Yeah. Okay, now again, going over the this not a number or none, NP none. This is not a number. You will, if you start your data science career, you will often get confronted with this concept of not a number. And not a number, this arises if you if you do something wrong with the data. For example, if you, I don't know, divide by a value that is not allowed or something. Yeah. So here we create an NumPy array consisting of 6 values, and 2 values of it take the specific value of NumPy.none, so not a number. And So something went wrong here. We have, for example, this can happen if you load data from a CSV file and the data is somehow corrupted, and your kind of the NumPy loading functionality, which I have not already introduced, but it's not so important here at this point. Yeah, it just replaces the corrupted data with this NumPy not a number to indicate that it's really corrupted. And now we want to kind of initialize two variables with 0, the student's present and student absent. And yeah, so the basic idea is to count the number of student present. So we go over all results in the data, student quiz results. Okay, no, sorry. Okay, so we have student quiz results, and some students haven't been at the test, for example. They missed the test, so they have not a number. And now we want to check how many students have basically this NumPy not a number. Basically, we simply want to count the not a number occurrences in our data set. Okay, so we iterate over the data. We check whether the result is equal to not a number, and then we add our results by 1, and so the absent, if it is not a number, we add we increment the student's absent variable. Otherwise, we increment the student's present variable, because then it is a number. So this kind of looks logical. It looks like we are doing the right thing, yeah? We check whether the result is not a number. But if we execute this, you will see that the result is different than what you have expected, because here we print the student's present variable, and basically it tells us that all students have been present. So it tells us, because we have 6 students and the result is 6, so basically we went into this branch in every loop iteration, in every loop cycle. Why does this happen? Because we didn't correctly compare not a number here, yeah? So NumPy is not a number value can't be compared to any other value using the equal operator, this one, equal operator, like in Python, since the comparison will always be false, yeah? So basically, if you want to check whether a value is not a number, we have to use the isNone function, yeah. So NumPy isNone function. This kind of is a syntactical thing, but yeah, it basically makes sense, because this equal operator, it checks whether they are basically referring to the same object, yeah. And of course, and this is not the case. I mean, they are not referring. So here we check kind of this equality which we wanted to check. Okay, so if we execute this code snippet, then I already told you it's correct. So what will be the output? How many students were present? Exactly 3 students were present, yeah? So we have 10, 7, and 5, 3 students. Okay, good. So let's move on. We are rushing over the puzzles very quickly. Now, how to create numerical sequences, yeah? So this is, again, the arrange function. So we have a variable x, we have the net worth variable, and so suppose this is our savings rate, and now we arrange, we go from 0 to 1000, and our step size is our savings rate, yeah? So how many months will it take to save at least $1,000? Okay, so what will be the result of this puzzle? Be careful to also account for boundary cases. So yes, the result will be 9. Yeah, because it takes in the first month you save. So basically, if we print, how can I show you? Maybe we can print the net worth. Okay. Now you can see it starts with 0, which is the first element. Then it takes 1 month, 2 months, 3 months, 4 months, 5 months, 6 months, 7 months, 8 months. But we also add this one, because now now the sequence does not contain values that are larger than 1000, but the question was, how long does it take to save larger than 1000? So basically, obviously this month is not a month on which we saved money. We should not count for this month, but we should still increase the number of months by 1 because we need one more month to cross the threshold of 1000. So therefore we didn't calculate -1 plus 1, we just used the length of this net worth array to calculate the number of months it takes to save $1,000. Okay, now creating numerical intervals. So here we first create a variable year. We use the linspace function. Okay, we use the linspace function to create a between the interval boundaries 0 and 365, this time included. You know, the linspace by default includes the end value, and we have 366 kind of sequence elements, which means that for every day we have one sequence element, so to say. Yeah, we have 365 days, and we start with but basically we have 366 elements because we add the 0th day as well. Okay, so now we convert the result of year -1, so the last value of the year, which is 366, and we deduct from this the value of year -2, which is 365. So the result will be 1. So let's run this 1. Okay. Good. Then move on to the next, initializing multi-dimensional arrays. Here we have our dimensionality 100. So we have 100 dimensions, which is really a lot of dimensions. And now we initialize. Basically, we don't have 100 x's. We only have 100 dimensions, like kind of, yeah. So it's this terminology is often confused. In this video, I use dimensionality and axis kind of interchangeably, but this was not a very precise expression because the dimensionality is different. So, for example, if you have 3-dimensional data, then you have a vector of 3 values. Yeah, so it's the number of values along each dimension here. Okay, now we create with W, we create the matrix of zeros. And we give the shape object, so we have 100, 100, and now we iterate over all indices of this dimension, and we set this to 2 basically, yeah. So we have a diagonal matrix, which on the diagonals we have some 2's. We have the integer values 2. And now we create another matrix with using 1's, which is with the same shape, and it only has 1 value. So it doesn't, basically it's a matrix full of 1's. And now we multiply those 2 matrices, but not using matrix multiplication, but using element-wise multiplication. Okay, and then we check the last element, and of course multiplying something with 1 will be 1. The last element -1, -1 along both axes, it will still be 2, so the result will be 2 as well. So this was a very simple puzzle, 2 as well. Okay. Now going back to some linear algebra stuff. Now still we have n equals 10, and we create this zeros axis and initialize it with 2, but now we use a new function I, and we use this dimensionality, and the I function basically creates a diagonal matrix, and this K kind of shows us the bias of the matrix. So basically you don't have to get it. Maybe I can show you in this scribble note, because it's difficult to explain but easy to show. Okay, now let's scribble a bit. So we have this. So here in this case we have a diagonal matrix where the ones are exactly at the diagonals, yeah. So in this case we have k equals 0 because we have no bias. But now in this case, k equals 1, it shows us basically the bias of our diagonals. Yeah, it will be, I think it will be like this. We can check later, but yeah, let me show you. Okay, 0, 0, 0, 0, 1, and then maybe this one. Actually, I don't know completely. I will check, but you see that the k is this a bias factor that shifts the diagonal matrix. Okay, so I will check this. A equals NPI, let's say 10, and k equals 0, and then we print A. Okay, as you see, we have a diagonal matrix, and now what happens if we shift k? Okay, yeah, exactly as I told you, with one difference, we don't have this, we don't kind of move the diagonal further on, yeah? So it's kind of here, the last row is completely zeroed out. So it's only the shift of the diagonals. And we would have to combine it somehow. If you want to have the k kind of proceed at this part of the, yeah, we would have to combine it basically. Like, I would say maybe we can do it. It's a good, so let's make it 5. Okay, and move this up. Okay, 5. You can see. Okay, now we have like this diagonal of 1s, and now we want to the 1 to start over here again and go downstairs this diagonal. And how can we do it? Basically, we create a new matrix I, and we use k equals -5. I guess this should work. I have not tried it out, but it's just online now, and now we add these matrices together element-wise. Yeah, so we should get, yeah, exactly. It works like this. So we have the diagonal here and the diagonal here, and it's kind of, yeah, this is the behavior I would have expected here when I told you that we have a 1 here. Okay, so now this works like this. Works properly. So the I basically gives us this diagonal matrix, and with 1s. And now we are doing some matrix calculations. But remember, everything is element-wise operation. So we have first we calculate 3 times m, 3 times the diagonal matrix with initialized with 1. So we have on the diagonals we have the value 3, and now we simply add our zeros matrix with 2 at the diagonals. So we have 3 plus 2 at the diagonals, which is 5. Now we check the last element, and the last element is also a diagonal element, so the result should be 5. Okay, this is the case. Now again, let's really hammer this down. The star operator is only the Hadamard. It's called a Hadamard product. And Hadamard project, so again, we have this data you have already seen of some data scientist, 2-dimensional matrix. Then we have the salary increase matrix. So for every year, for every job description, we have kind of a multiplicator. Now we simply multiply this. So we are not doing matrix multiplication, but we are doing element-wise multiplication. Now we check for the second, so basically the third element, which is the designer. In the first year, we check whether, basically this notation seems strange to me. We could also have used the comma here. I don't know whether this really works. Okay, but let's check it in a moment. Okay, and we check whether our new matrix, whether basically the designer in the first year has gotten a salary increase, but actually we multiplied with 0.9, so the previous salary would be larger. So we have the previous salary is 118, the new salary is 118 times 0.9, so it is smaller. So the result should be false. Let's run it. Yeah, the result is false. Basically, I don't know, this notation here in NumPy also seems to work, that we for each dimension we give it our own bracket notation. Maybe it's cleaner in some areas, but I would always prefer this comma separated dimension notation. Therefore, I was a bit confused now. Okay, multiplying two elements element-wise. Now we have, yeah, basically this is more or less the same. I will skip this puzzle. Then we have, no, it's basically this puzzle is it's very interesting. Sorry, this is yeah, it's in this case we have we create one matrix A. Okay, maybe I'll show you in a separate example, because this is really an interesting example. Okay, so now we have A is an NumPy array, say of 5 times 5. No, don't be confused. It's just 5 times 5. So we just create an array with value 5, yeah? And now we calculate we want to multiply this array with, say, 2.0. Yeah, so we would expect basically element-wise multiplication. So every element of our array should be multiplied by the value 2. Okay, and the result is obviously nothing, because I haven't printed the result yet. The result is that we have floating points and 10.0. But actually this is a bit surprising, because also you wouldn't expect that this works somehow, because here on the left hand side we have a NumPy array, on the right hand side we have a float value, so not a NumPy array. But NumPy, for all operations, it always assumes that we have two NumPy arrays that get multiplied together, so they get aggregated. So basically internally what NumPy does is to create a NumPy array with the following shape. So we have 2.0, 2.0, 2.0, 2.0 and 2.0. Yeah, so we have internally NumPy creates a new NumPy array and kind of copies the data. It does not really copy the data for efficiency reasons, but it's conceptually copies the data and creates a new NumPy array out of this. And yeah, so, and then it, as you know, it performs element-wise multiplication. So now everything makes sense, and the result is exactly the same. Yeah, because this is now kind of, we have performed one step of NumPy's automatic type conversion, yeah, internally. And this type conversion is called broadcasting. There's some rules to broadcasting, but most of the time your intuition will tell you what NumPy does, basically. Okay, it's kind of clear if you use a floating point here that it will be broadcasted to an array with the same shape on the left hand side. And even if you have two-dimensional array, then this will still work. So we have this two-dimensional array, okay, now we have this sequence of not integer. Okay, I think maybe I have to write it in the conventional way. So we have this 5 and we have 3s. Ah, yeah, okay. The problem was that the shape didn't match. Okay, so now in this case we have the same number of columns for each row, which of course should be assumed always. Okay, so now we have this. So basically we are multiplying. We have this A array, which is the 5s and the 3s, and we multiply it with 2. And basically what it does is it internally creates a two-dimensional array with exactly the same shape, copying the value 2.0 to each position. So we have like this array 2, 2, 2, 2, 2, 2, 2, and so on. Okay, so the two values copied. And this kind of, I want to stretch this discussion a lot, because to hammer it in your brain, that the term for this is broadcasting. Only advanced NumPy coders will know the term, even broadcasting. They will know what you mean. But if you want to dive deeply into data science and NumPy, you need to understand broadcasting a lot. And yeah, but I mean, just know that most of the time it will do what you expect it to do. Sometimes your code will crash, and in this case, you should look into the assumptions you made, how NumPy broadcasts your arrays, so how it automatically extends your arrays. For example, here we have the same data. We have a two-dimensional array of salary data for 3 years and 4 positions, and now we create a new array which has 4 rows and 1 column. Yeah, and so it's a different array, it has different shape, but here we are performing element-wise operation. So now in this case we have the value. So basically, let me scribble this, what we are doing here. So basically we have this one array which has shape 4 rows, 3 columns, like we have 1, 2, 3, 4, and 1, 2, 3. Okay, so like this array, this is what we have: 4 rows, 3 columns, and we have, in this case, we have an array with 4 rows and 1 column. Yeah, so we have 4 rows and 1 column, so like this. So now, how does NumPy broadcast? So how does it actually fill? So NumPy has to fill the remaining columns so that both arrays have the same shape. Yeah, you see? So how would you do it actually? If you were NumPy, how would you fill the remaining cells so that those two arrays can be multiplied element-wise? Yeah, of course you would copy this column, basically this column, you would copy and move it, and yeah, copy it into every column here that is remaining. Yeah, and this is exactly what we are doing here. Yeah, so we have this array A and we have the array B, and the array B is a column vector and it is copied. Then so we have some ones and ones and ones and ones, and we set the first value of this column to 1.1. So we have 1.1, 111, 1.1, 111, 1.1, 111, and so on. Yeah. Okay, and now this basically means that the first row we multiply with 1.1, and now the resulting matrix we get the first element, which is 130 times 1.1, so plus 13 basically, which is 143. And we convert it to an integer, so this should be the result. So let's run it. 143, yeah. You can see it works like this. Okay, now we are going on and practicing simple NumPy indexing. And yeah, here we have some air quality data. This is the AQI index data for air quality index. And yeah, for 3 cities, you can see Hong Kong has a higher value, which means worse air quality. Now we simply kind of do some basic operations. We calculate the first element of the Hong Kong data. So here the first element, we have 42 plus the last element, which is 43, and then divided by 2. And we have the resulting value is the float. So the first will be 42.5. Then the second will be, we take the second element and minus 3. So we take this element of New York and the third last. So this would be minus 1, minus 2, minus 3. So we have 31 plus 22, which is divided by 2, which is 30.0. And for Montreal, we take the second one and the first one. Minus 0 is still 0, so the 0 will be the first element, and this one, and the average is 11.0. So our result is 42.5, 30.0, and 11.0. Then we have the Boolean indexing trick. I have shown you this trick previously. We have the years, we have the leap year indices. So some years are leap years, and for example here we have true, false, 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 true, false, false, true, and so basically every 4th year is a leap year. And now we access years with leap indices. So most of them will be 0. So we have 3 elements coming back. The last one will be this, 2008. Okay. Then we slice matrices. This is a kind of an advanced slicing technique. I don't want to go too deeply into this because it takes some time. It's kind of this is really a puzzle you have to figure out. So only, I mean, you can see we are slicing. We start with the 2nd, we stop with the 5th element, not included. Then we do some negative indexing. This is kind of, this has to be done. You have to do it in with time. So get the book and do it with time. Okay, then we have some simple array logics here. This is interesting as well, because here we have a simple one-dimensional list. We create an array out of it of Instagram followers. Like here, for example, Instagram itself has 232 million followers. Then Selena Gomez. Actually, I don't know most of the names here. Okay, I know Beyoncé and Nike and Cristiano Ronaldo. I don't know Victoria's Secret. I don't know Selena Gomez. Okay, so but they are really there are some popular Instagram people. And yeah, then we want to basically we create a new NumPy array. And what are we doing here? We're comparing an array whether it is larger than 100. So can you already see what we are doing here? Basically, again, as I told you multiple times in this tutorial, NumPy expects that you have arrays of the same shape when performing some element-wise operations. But here, obviously, these two don't have the same shape. This one is an integer, this one is a NumPy array. So what are we doing? We are broadcasting. NumPy broadcasts this value to have a one-dimensional array as well with only 100 values, 100 integer values filled. Yeah. And now we do element-wise comparison. So we check whether our Instagram followers, whether they are larger than 100. And then we have a value true, otherwise we have a value false. So our array is a Boolean array. And yeah, now we check the first one and the 3rd element. The first has more than 100, the 3rd not. So we have true and false as a response. So let's check this. True and false is correct. Then slice assignment. This is also an interesting puzzle. It's short but sweet. So we have the Fibonacci series. If you don't know the series, it starts with 0 and 1, and then we just add the series element, the 2 last series element together to get the next series element, which is 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. Okay, and now we use slice assignment. So we select some values here, every 3rd element. So we select 0, 2, and 8, and we replace it with 0. Again, we are doing broadcasting here. And now we calculate the sum of all elements starting from the 1st and ending in the 4th element. So we have the first 4 elements, and we have replaced this one and this one with 0. So the result will be 2, 1 plus 1. All the other elements are 0. So let's execute it, 2. Okay. How to sort an array? Again, we have some quiz scores, a one-dimensional array. We now we simply sort the array, and here this is kind of the trick here, that we are using slicing with negative step size to transform the array from an ascending sorted series. So previously it was ascending, now it's descending. Yeah. So, and of course, then we take the second last element of the descending array. So let me quickly. Okay, so basically we have the sorted array has the element 5, 6, 7, 8, 9. This 5, 6, 7, 8, 9. So it's ascending. Then we move the series around. So we have 9, 8, 7, 6, 5, and now we take the second last element. So we have 6, 5. 6 is the second last element. So execute this. 6 is the result of this puzzle. Good. Then the next puzzle is also about sorting, but we are using arcsort, which I have already introduced in this tutorial. So we have some IDs and some values. Yeah, so we have kind of like sensor IDs, for example, sensor ID 56, sensor ID 61, and so on. And then we have some values. So suppose we have kind of distributed some sensors in the Internet of Things, and now we have some measurements, and now we want to sort them. Maybe this is a radioactive poison, checks how poisoned a certain area is, and now we want to sort, obviously, and now to check what are the most dangerous areas. But if we simply sort the values, then the values are sorted, but we don't know which sensor ID basically is the dangerous one. Yeah. So we are using arcsort. We sort values according to the value. So the result of the sequence would be 6, 7, 8, 9, 10. Then we use the arguments. Yeah. And we take the ID of the of the third element in the sorted series, which is 6, 7, 8. So the sensor with value 8, this is the element that's at position at the third in the sorted sequence. This is the third element. 6, 7, 8, yes. And this element has ID 33. So we access ID 33. We access this. Yeah, this ID. Okay, so let's run it. 33 is the result. Okay. Computing array element differences. So again, we have the Fibonacci series. Now we calculate the difference between the Fibonacci series elements. Yeah. So you know the difference is this 1 minus 0 is 1. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 2 is 1. 5 minus 3 is 2, and so on. And now we simply want to know the fourth difference value. Okay, so this was the first one, second one, third one, and the fourth. Actually, the fifth one we are searching, yeah, which is 2. Okay, because 0 is the first sequence element of this diff series. Okay, so and we calculate 5 minus 3 is 2, so the result is 2. Good, moving on. Computing array of cumulative sums. So we have some array donations, and now we accumulate the array. We calculate the cum sum of the donations. So we simply calculate 2 plus 3 is 5. Then in the next element will be 2 plus 3 plus 2.5, and so on. Yeah. So we have this cumulative sum, and now we want to have the minus fourth element. So we start with so the first element will be 2, the second element will be 5, and so on. So we have exactly the same number of elements as here. Minus 4 means we are at which position? Minus 1, minus 2, minus 3, and minus 4. We want to have this element, so which means we have to sum everything in front of this element. So we have 2 plus 3 is 5, plus 2.5 is 7.5. Let's check whether I was correct. Yes, okay. Okay, move on. Calculating the 1D dot product. Good. This is now the puzzles that are coming now. They are a bit more about the basics of linear algebra and statistics in NumPy. And yeah, basically the dot product. You have to know the formula to calculate the dot product, and we have this simple regression. This simple regression model of W, then the stock prices, and the prediction is the dot product. Also, we calculate W times X using the dot product, and if our result is larger than the first value, which is kind of the value where we bought, we print buy, otherwise we print sell. And now we calculate like 0.7. You can already see intuitively that the prices are basically, so here the prices are basically more or less they are rising, I would say, so we should buy. Okay, So I have not calculated it now, but the prices are rising, so we should buy. Let's run it. Buy. Okay. So matrix multiplication. Here we have some graphics data, and now we have something new. And the new thing is, so you have already learned about the matmul operation. So this would be a graphic example. So we have some graphics data. It could be some pixel values. Pixel is either set or not set. Then we have some stretch vectors. So we have the diagonal values are 2. So we stretch every like of column vector, we stretch it by 2. And now we calculate the matrix multiplication. And now you have to know that the syntax of this add operator is basically the matrix multiplication itself. So this is the one thing you should get from the puzzle, that the add operator is the same as the matrix multiplication operator. And if you do, then you see, okay, now we are comparing two arrays element-wise. So we have a Boolean array, and now we want to have the first element of the Boolean array. And of course, as the arrays are equal, it will be an array of true Boolean value. So the first one will be true as well without calculating it, basically. Okay, now we have true. Now enhancing vector operations with NumPy arrays. We have 2 points in the 3D space, like point A and point B. And now we calculate simply B minus A, very simple. And then we perform the squad operation. Squad, so it means, yeah, you know squad. Of the sum of the resulting array squared. Yeah, so now this is just a matter of calculating it in your head. I won't do it now because I'm a bit, maybe let's do it. Let's do it, why not? So we have, first we calculate, we have 1, 0, 2. And now we calculate 1 minus 5 is minus 4. 0 minus minus 3 is plus 3. So we have minus 4 plus 3 and 0. Minus 4 plus 3 is 0. And now we square it. So we have 4 times 4 is 16. 16, 3 times 3 is 9. So we have 16, 9, and 0 as the result. 60 plus 9 is 25. Squared, so 25 the square root is 5. And now we convert it to an integer value, and this gives us the length of our vector, and this is 5, obviously. Okay, so now run it. 5. Okay, linear algebra made simple. So we have again 2 vectors, the cross product. Now you also have to know the cross product here to calculate this. And yeah, now this we won't do. Basically, I can show you a figure which is drawn by one of my co-authors of the book. What we are doing here is, yeah, we check whether the two vectors have 90-degree winkel. I don't know the English word, and yeah, whether they have a right angle. Yes, the right angle, and this is done by the dot product. And yeah, if you calculate it, you will see that the correct solution is 0. Yeah, scalar product is 0. So yeah, some linear algebra magic that happens here. You can read the description in the puzzle. Good, then going to the average. Here, this is, I created this puzzle in the last World Cup, Football World Cup. So we have goals Brazil and goals Germany. You see Germany has shot a smaller amount of goals in average. So we have 5 matches. Brazil usually has a very strong offense, so they shoot a lot of goals. So the average of Brazil's goals is obviously higher than Germany's goals. So true is the result. Then now this here I will skip this puzzle, and now we are going the average. I will also skip this average puzzle. This one is interesting. Here we have the weighted average. Again, we have the SolarX stock price. So SolarX is the company of Elon Musk, and we have the stock price of today and yesterday. So this is the morning price, the midday price, and the evening price. And now we want to calculate the weighted average of every midday price of the midday prices. Okay, so basically what we are doing here is we call NP average on the solar axis with the axis on the solar x stock with the axis parameter set, so along axis 0, which is the vertical axis. So we aggregate the vertical elements, like we average 2 and 2, we average 3 and 2, and we average the two values 4 and 5. Okay, but we don't use a simple average, but we weigh the values. Yeah, so we take the first one had 3 quarters, and the second value has only 1/4 of weight in this average computations. Yeah, so this one has 3 times the weight. Okay, so we have 3 times 2 is 6 plus 2 is 8 divided by 4 is 2.0. 3 times this is 9 plus 2 is 11 divided by 4. 11 by 4 is 2.25, and this is basically the result that is printed here. Let's check this. 2.75. Okay, this was wrong computation, but yeah, you know, 11 by 4 is 2.75. Yes. Okay, so now we calculate the 1D variance. So it's just a matter of calling the variance function. And again, we have this axis parameter and standard deviation, and then we have some statistical operations. Here we calculate the mean. I think you haven't seen the mean yet, but yeah, in this case, the mean value is clearly similar to the average, yeah, because yeah. Actually, I want to check. I have to check this, because say we have an array 3, 3, 4, 5, 5 like this. Now let's make it 5, 9. Now NP average A and mean A. Okay, it's the same here in this case. Okay, mean and average is the same. Okay, then yeah, we calculate the mean of the sensor data and the standard deviation of the sensor data, and then we simply print out basically both values. It's a very simple computation that can be done by you. Then we have a faulty sensor value. Here we clean the data by simply slicing over. We simply ignore the faulty sensor data, and then we calculate the mean. Here, this is some filtering, and this I will maybe we will do this puzzle again. So we have the Boolean array of 3 Boolean values: true, false, true. Now we sum over all values in the Boolean array. How can this be done? For this, you have to know that the true value in Python is represented by an integer 1, and the false value is by default represented as an integer 0. So we have 1 plus 0 plus 1 is 1. Is 2. So we have 2 is larger than the sum of those. But basically it's the same. 2 is not larger than 2, so the result is false. Okay? Creating filters. Now again, we have some student grades, and I think the interesting part here is that you can also use comparison on strings. Yeah. So because I mean, intuitively D is is larger than A, for example. So if the grades is larger than D, which means only E, then, or E and F, I don't know how many grades there are in US, but I think it goes on to the F. Yeah, if the grades are larger than D, then they do not pass. So then we filter out these students. We take the first. So the first student B, so he is not larger, so this is false, and this one, the last one, is larger, so this is true. Okay, so now run it, false and true. Okay, now moving on, the power of filters. This is a bit more complex. It uses list comprehension, an advanced feature. So we have 4 books. like each book has one row. You can also define a row as a tuple. This doesn't really matter for NumPy. Internally, it's still a two-dimensional NumPy array, and the books have some ratings, 4.6. And now we have a bestseller filter. He takes basically, this is the expression, so it's list comprehension. We create an element after this expression for each x in rating. So for each row, we add an element to, according to this formula, to the list. And the element is basically a true value. So we check float. So we convert the first value, so this one, 4.6, to a float value. And we check whether it's larger than 4.5, which is true for the first element, false, false, true. So we have 4 elements, true, false, false, true. And now we check. And now we have true, false, false, true. And now we apply this to our ratings variable. So we have true, false, false, true, which means that we select this element and this element, 2 elements. Now we check the length. So we have 2 elements. This is the number of bestsellers that have larger than 4.5 ratings. Okay, 2. Now this can be also done for two-dimensional arrays. I will skip this and skip this too. This is a very interesting puzzle, but I will skip it. Here we have some. This is also a bit more complex to explain here. It's basically about collaborative filtering. So to predict what products customer will buy, given that customers who bought a certain product also bought another product. So it's motivated by Amazon, for example. It will frequently recommend you product bought by people who bought products similar to your product. So you are getting kind of calculating this collaborative filtering is done here. These are really very practical data science applications. So the puzzles are becoming now much harder, as you can see, but I will skip them. You can read them in the book, but they don't even fit to this Jupyter notebook, so we will skip them and this as well. And I think so. These were all the puzzles. I think this was a very thorough and broad introduction to the NumPy library. And now I went over most puzzles in the book. But of course, the book has much more topics and explanations, and it's very deep introduction to the NumPy library. So I hope that you like this puzzle-based learning scheme, and I think you should take your time to dive deep into the puzzles to find your own answers. At the point you bought the book, you have already forgot about the answers I gave you, so you should kind of take your time and let the thought processes run smoothly. Okay, so thank you very much for your attention. It has been fun to talk to you. I would love to hear your comments, whether this video was helpful to you. If so, please leave a comment with yes, otherwise leave a comment with no, so that I can get some feedback. If it was helpful for many people, I plan to do those very long, deep introduction into topics in the future multiple times. And of course, if you want to get notified, then please subscribe and hit the notification bell so that you can learn about new videos that I will release of these deep introductions and tutorials. I think many YouTube videos are actually very shallow, and because YouTubers try to focus or minimize the time spent for some videos, like they would rather create 5 videos with 10 minutes than 1 video with 50 minutes, because then they get some more traction on the YouTube channel. But I don't follow this strategy. I want to give you a very deep and very thorough education. So this was the strategy with this video. I hope you like it, and if you did, then again, give it a like, subscribe, and get the book. Thanks for watching.